Anyways, my first talk, it's inspired by the method of diagrammatic Monte Carlo, though I will not be describing the method itself. I will be describing something else very relevant to simulations with diagrammatic Monte Carlo. So let me formulate the problem. So we have two paradigmatic models: uniform electron gas, also known as Jello model, repulsive Hubbard model. And what we know about those models is that they do support superfluid phase transition relevant to superconductivity. However, the temperature of this transition is extremely low compared to the characteristic parameters of the model, meaning that the superconductivity, superconducting transition happens on top of the Fermi liquid behavior. So there is a huge interval of temperatures where the system behaves as a normal degenerate Fermi liquid. Meanwhile, the microscopic physics is strongly correlated. So it's not easy to produce a controlled answer for the low temperature but analytically. We need to embark on numerics, and we do have such numerics. It's diagrammatic Monte Carlo. And the problem with diagrammatic Monte Carlo is that it's good at high enough temperatures, which are much lower than, say, Fermi energy, meaning that we can nicely simulate Fermi liquid regime. But the problem emerges when we want to do superconductivity by the brute force. The problem is with convergence, because diagrammatic Monte Carlo deals with diagrammatic series which becomes divergent at very low temperatures. The idea which I'm going to introduce is based on physics. So it turns out that actually this normal Fermi liquid state knows everything at temperatures orders of magnitude higher than the critical one, everything about the Cooper instability which is going to happen in this or that channel, or about its absence. The key point is, how do we extract this information? And to give you a heads up, we can extract this information reliably. I will show you the examples from the response to the uniform pair creating perturbation. This is also interesting, by the way, in the context not only of numeric simulations, but also emulations, quantum emulations with ultra-cold atoms. Probably you know that nowadays ultra-cold atomic experimentalists can create a repulsive Hubbard model with ultra-cold atoms in optical lattices. They can create the model, but there is absolutely no way they can go to temperatures which are orders of magnitude lower than the bandwidth and the Fermi energy. However, if they create a uniform perturbation, pair creating perturbation, in principle with ultra-cold atoms you can do that. You are not supposed to really create two particles. You can just change the internal state of them. That's how people can, with ultra-cold atoms, can emulate the pair creating or just particle creating perturbations. So in principle, it's a dual protocol. So this is yet another aspect of interest why what I will be telling you might prove relevant to emulations. So let me remind you something which maybe you know even better than me. So what is the standard approach to the problem of finding the critical temperature of Cooper instability in general, and in particular if it emerges in the BCS type regime? So we start with modifying the Hamiltonian by adding the pair creation perturbation, like here. Eta is a certain perturbation, just a certain function which respects the symmetry of the channel. So Raphael introduced us to kind of many different channels of superfluidity. So this guy is such that it selects a specific symmetry channel being related with the rotational symmetry or point group of a lattice, whatever. So we are always talking of some specific channel, though for simplicity I do not introduce corresponding projectors and stuff. So, and then we observe the following average. It looks like an anomalous average, but in our case it's not, because we explicitly break the symmetry of our Hamiltonian. And then if we calculate this guy diagrammatically, so in the left-hand side we have this guy, in the right-hand side we have this perturbation and the whole diagrammatic series, but the whole diagrammatic series can be actually combined into the following structure. Two Green's function, some vertex gamma. Once again, I believe that everyone knows what it is. It's Cooper irreducible vertex, and the average itself. So essentially, we end up with the linear equation. Linear in terms of this observable, because this eta is supposed to be small enough. And essentially, if I take everything to the left-hand side in terms of my my response, I get the linear equation with the right-hand side in homogeneous linear equation. And now one solves this equation, though the whole point, which I will be discussing, will be about, or at least one half of what I will be discussing will be about this right-hand side. So the importance of solving this equation rather than the one which I will be discussing next, the one which everyone solves. So people say, OK, here is the equation, but typically, if we are looking for the critical temperature, we do not care about the response itself. We care about the temperature, the point at which the response becomes singular. And since it's just a linear equation, all we need to do is to find the zero eigenvalue of the operator in the left-hand side. And since we have two terms, one of which has just the unity operator acting on our guy, and yet another operator acting on the very same guy, it amounts to saying that we are looking for the situation when this operator acting on a certain vector. See, the color is red here, meaning that as opposed to the response in general, we are looking for a certain eigenvector, which is denoted with the red line, which corresponds to the eigenvalue which is unity, in which case unity minus unity is 0, and we have a singular response. That's how we arrive at what you see here, and this is nothing else but the linearized gap equation. We need to solve this linearized gap equation and find lambda, and the temperature at which lambda is unity is just the critical temperature. This is the standard, absolutely standard textbook setup of the problem. Now, if we were dealing with effective theory, with BCS type theory, everything would look as follows. So our Green's function would have the standard Fermi liquid ansatz. Our effective, not to be confused with microscopic, irreducible gamma would be very simple. It would be just independent of temperature and frequency something, in which case all the temperature dependence would be coming from just these two Green's functions, and essentially the temperature evolution of this eigenvalue would be very simple. Here it is. It's just the logarithmic dependence on temperature. Probably you've seen this formula many times, and that would be the expression for the critical temperature in terms of this logarithmic dependence with a certain cutoff. So in the terms of the effective theory, everything looks very simple, good, and essentially immediately solves the problem of extrapolation. So the point is that if we would know this effective gamma somehow from some simulation or whatever calculation, we would immediately be able to extrapolate this lambda from solving this problem to the relevant temperature at which this lambda becomes 1. Everything would be very simple, but it turns out that it does actually work with the theory which is microscopic rather than effective. So the dependence of lambda in an actual theory is different, and that's the problem. So let me just start with a certain refinement of the problem. So instead of this eigenvector, it's also a very standard, by the way, a very standard procedure. And basically, when I'm saying linear gap equation, I mean this particular equation, not just the previous one. When I transform my vector in such a way that I introduce a new quantity, I use the very same notation delta as for the gap function. Sometimes it's called the gap function. So essentially, that's how my equation looks like. But the principle is the following. So I can solve this equation with diagrammatic Monte Carlo. I can find this lambda, but I am not able to extrapolate this lambda, reliably extrapolate to the critical temperature, because its temperature dependence is not the one which we saw on the previous plot. So this temperature dependence is different from the simple temperature dependence of lambda bar. And here comes the problem. What can be done? Of course, you can say, oh, but why don't we calculate the effective gamma? The problem is that calculating the effective gamma with diagrammatic Monte Carlo is very hard because it's a multidimensional function. So with diagrammatic Monte Carlo, we can calculate some simple objects like Green's function, self-energy, some observables. If you have a many-body function, it's virtually impossible to calculate it, because what we do, we sample the functions. Obviously, sampling a multi-component, histogramming a multi-component function is very difficult. That's why we created a protocol. We came up with the idea of a protocol which is called implicit renormalization approach, in which case we do something which is equivalent to the renormalization, equivalent to producing the effective gamma, instead of just explicitly calculating it. So let me introduce you to this protocol. So first of all, let me remind you what is the, maybe once again you know it better than me, what do we mean by renormalized gamma, by effective gamma. I denote it with gamma bar. So as opposed to the microscopic Cooper irreducible gamma, we need to do the ladder diagrams living in the Green's function loops, the higher energies, the high frequencies, excuse me, and momenta. So the low frequency and low momenta are the part of our effective infrared theory. The higher ones should be actually summed up. So that's essentially what we need to do. But as I said, we cannot do it explicitly, because the objects are multivariable, too difficult to treat numerically. And that's the trick which we can use. So first of all, let me just introduce some convenient matrix vector notation. So delta is a certain vector, by which I mean the object which depends on the momentum and frequency. Frequency is a Matsubara frequency. It's discrete, but for simplicity, I treat it as a continuous. And that's the equation which we want to solve, the eigenvalue, vector equation. And what we do, we actually separate the eigenvector in two pieces, the low energy part and the high energy part. Just introduce some separation of the scales as shown here. We essentially separate everything into two pieces and write everything as a block matrix. So far it's just a rewriting, nothing special. But yeah, yeah, please go ahead.
So when you write all of your diagrams, you always write the full Green's function. It's the bold Green's function which contains all the vertex corrections, everything.
Yes, everything. We can simulate it. Well, technically speaking, we simulate the self-energy, then convert self-energy into the Green's function by the Dyson's equation, right? So, yeah. So the Green's function is something which we know from simulation. The vertex function is something which is being sampled, because the Green's function is simple enough. It's just two variables. Yeah. Right. It's an exact, numerically exact Green's function. Yeah. So now look at this its equation, which so far was just rewritten. Here it is. And now let us formally replace this lambda with unity. So what happens? In terms of the critical point, those equations are equivalent, because remember, at the critical point, lambda is equal to 1, meaning that whether we find a solution to this equation when lambda is equal to 1, or we find a solution to this eigenvector problem, obviously this eigenvalue is different because you see here is unity, but the moment this guy is equal to 1 and this guy is, equal to 1, the problem is solved, because when either lambda or lambda bar are equal to 1, we have identically the same equation. But the point is that as opposed to this lambda bar is exactly the eigenvalue of the effective theory. That's why we call it implicit renormalization. So it turns out that if we solve this problem effectively, we are solving the problem with the interaction which is renormalized. And let us see why. So you see, with this equation, I can actually express this high energy part of the eigenvector in terms of the low energy part, right? Because I just use this equation. And then I plug it into the upper equation and see what happens. So as a result, I have the equation for the lower energy part only with a new operator which has the following form. But this operator is exactly the kernel of the effective theory. So this operator is exactly the effective vertex gamma bar, which we do not calculate. Numerically, we just sample this equation. So what I sweep under the carpet is the numeric protocol of solving this equation. But just trust me that with diagrammatic Monte Carlo, we can do that. We can just sample the equation as is. So that's essentially protocol number 1, which we can use. And let me give you an illustrative example, the simulation of the three-dimensional uniform electron gas. So that's the plot which shows that lambda bar indeed scales linearly with the log of t, as opposed to lambda. So I do not show you the result for lambda, but trust me that it's not a straight line. So what we do here, we take a three-dimensional uniform electron gas at a certain parameter of Rs, which was already discussed today. So essentially Rs, the Wigner-Seitz parameter, is the radius of the sphere containing exactly one particle. So it's essentially a sphere with the radius which corresponds to the volume per one particle. However, it's a dimensionless parameter because the radius is supposed to be expressed in the units of Bohr radius. So when Rs is small, it means, or equivalently, you can say that Rs is on the order of the characteristic interparticle distance in units of Bohr radius. So if Rs is small, then we are dealing with a weakly interacting system, because with a Coulomb system, probably you know it very well, the weakly interacting limit is the limit of high density when the interparticle distance is much smaller than the Bohr radius. Rs order 1 or 2 is not that weakly interacting system, but in this case we are not interested, and actually we are not doing yet full-scale diagrammatic Monte Carlo simulation of gamma. We use an approximation, because our goal here is just to demonstrate that the principle works, that some faithful, meaningful representation of the irreducible, Cooper irreducible gamma does the job of kind of demonstrating the linear flow. So we are not supposed to kind of take this result as a controlled result for the critical temperature, though it might be good enough, because essentially we have the following argument that our results are reasonably meaningful. We can do the RPA approximation for the irreducible gamma, and we can also do what is known as Kukkonen-Overhauser approximation, which is more sophisticated, and we can compare the two, because if the two produce more or less the same, we believe that with reasonable kind of degree of confidence, the systematics is not that big, because obviously KO, Kukkonen-Overhauser approximation, is not the same. It's far more sophisticated than just RPA. So what we see here is the simulation for the L equals 3 channel of pairing, and essentially that's the demonstration how this protocol works. And essentially what we extract from this line is the critical temperature. Pay attention that the critical temperature is extremely small. It's 10 to the minus 20, and it's, if you will, this kind of small number is the demonstration of power of the method, because obviously by the brute force we cannot go to that low temperatures. Meanwhile, we can reliably estimate this temperature, because this guy is just a straight line. So kind of that, yeah?
What are the units of TC?
Fermi energy?
Yeah, sorry. I mean, like, you said it's really small, but like.
Oh, it's relative units, because you don't care about the absolute unit depends on the density, but yeah, but it's irrelevant, right? It's irrelevant. It's irrelevant because we are not talking of actual electrons. We are talking of some particles with Coulomb interaction, meaning that the only parameter is Rs. Yeah. You can always recalculate it. Yeah. No. You just still nothing. So it's the temperature in units of Fermi energy, but the only physically meaningful parameter is Rs. Okay. So conclusions from this part. So this is one of the protocols. I will introduce you to yet another one, which in terms of physics is even kind of more instructive, I would say. Because you see, this one was purely numeric. Experimentally, obviously, you cannot address, if you are talking of emulations with ultra-cold atoms, obviously you cannot address the pieces which were introduced purely diagrammatically, like Cooper irreducible vertex. So we were supposed to deal with something kind of physical rather than mathematical. So the conclusions from this part is essentially the following. We do have a protocol which allows us to extract critical temperatures which are orders of magnitude lower than the temperatures at which we perform an actual simulation. The implicit renormalization provides us with an unbiased way of solving the problem. And in particular, with this protocol, we can extract the actual form of the eigenvector corresponding to the emergence of superconductivity. So we actually, as a byproduct of the method, we extract the eigenvector corresponding to the Cooper instability. So despite the success of this method, there are shortcomings. So suppose our channel is Cooper stable. We also want to tell a Cooper unstable, apart from just telling what is, apart from understanding what is the critical temperature of Cooper unstable channel, we also want to answer a question of Cooper stability. We want to say whether the channel is stable or unstable, and in particular, we want to find the quantum critical point at which, as a function of some parameters like parameter Rs, in the case of the uniform electron gas, at which this or that channel becomes stable or unstable if we change the control parameter. And you see, the whole idea of the implicit renormalization was all about dealing with Cooper unstable channel, because it was focused, the protocol was focused on the behavior of the eigenvalue, which essentially become problematic if we are in the vicinity of the quantum critical point at which we change the stable channel into unstable. So the alternative approach, I already announced it, is based on tracing the linear response function. So to do that, first of all, let me just announce the bottom line, and then I will proceed with the derivation. So something is well known about the linear response. So the linear response function, chi naught, is just the average, which I was demonstrating on one of my first slides, divided by the strength of the perturbation. So what is known, very well described in literature, is that on the approach to the critical point, the susceptibility diverges according to this law. So this is good, but not enough, because it doesn't allow us to deal with temperatures which are orders of magnitude higher than the critical one. And here is the reason why. So I will explain later that this is the actual ansatz, the actual form, the three-parametric form of the susceptibility. So you see, if we compare this accurate answer with this formula, excuse me, we will see that somehow this formula ignores the numerator, which contains the very same log as the denominator. So what is kind of the physics behind this formula? So it's interesting that there are two very different pieces of physics. So suppose I ask you a question: what is the response of an ideal Fermi gas, non-interacting Fermi gas, to the pair-creating perturbation? And it turns out that this response is singular at zero temperature. Just calculate, make a trivial calculation, introduce the term which breaks the symmetry, and observe that as temperature goes to 0, the response function diverges. Say it again? As a function of temperature.
Just the magnitude diverges.
The magnitude diverges, right. The magnitude diverges. It's not the answer diverges, but the magnitude diverges. And the divergence is just this log. That's how it diverges. So this numerator is nothing else but the behavior of an ideal gas. This denominator takes care of the interaction. So in the absence of interaction, this G is just equal to 0. So the Cooper instability is all about the side of this effective dimensionless parameter characterizing the interaction. So if G is much smaller than 1, actually we do not even, to the leading approximation, we do not even see the difference between Cooper stable and Cooper unstable channel. So if we just naively look at the main term of the susceptibility, we just observe the behavior of an ideal gas. So we really need the whole ansatz to be able to tell the Cooper stable from Cooper unstable channel. Just think of the situation, because you see this guy by definition is small. That's the definition of the emergent BCS regime. Otherwise, it's something else. So when this guy is much smaller than unity, this log, and log is never large, kind of, compared to something small. So the whole thing, this thing, stays small over a huge interval of parameters, and we just observe the behavior corresponding to the ideal gas. However, if we know the ansatz, we are able to see this correction. We are able to see this correction, and we are able to tell the difference. Pay attention that the Cooper stable channel is also interesting, because as opposed to the ideal gas, so naively we would say that, oh, if there is no Cooper instability in a given channel, the behavior corresponds to the ideal gas. That would be our standard logic of Landau Fermi liquid theory. The answer is no. The Cooper stable channel does something else. It actually suppresses this divergent numerator, because if this log is appropriately large, so that this term is substantially larger than unity, the response in the Cooper stable channel does not evolve with temperature any longer. So it means that in a Cooper stable channel, the system does something also interesting. So it actually suppresses the zero temperature singularity of a non-interacting gas. So call it anti-Cooper effect. So developing correlations which actually suppress the susceptibility, or rendering it essentially finite. So let us proceed with the derivation of what I just announced. And as a byproduct of this derivation, we will actually figure out that there exists an even better observable, though this better observable will be of purely diagrammatic nature than the previous one. In the previous one, we had 3 fitting parameters. In the new one, we will have only 2. It will emerge naturally as a byproduct of our derivation. So let's get back to the statement of the problem, to the setup when we have a perturbation, when we have the Hamiltonian. So you've already seen this stuff. And rather than doing the eigenvalue, eigenvector problem, it's just a reminder of how we introduced a new quantity, the eigenvector. We will actually be honestly solving the problem of the linear response. However, we'll be using the very same mathematical trick of introducing a new quantity, call it R. The formula is the same as for the quantity delta, the linearized, which was the eigenvector of linearized gap equation. But the reason for introducing a different quantity is because now my equation is not the linearized gap equation. It's not the eigenvalue eigenvector equation, but it's an equation which produces the actual linear response. So I do have the right-hand side. So I'm not solving for eigenvectors and eigenvalues. I'm just honestly solving the problem of a response. In which case, actually, I can set this eta to unity, or it's better to say to unity in the corresponding channel, because remember, we have the very same equation projected on each symmetry channels. But kind of for simplicity, just think of just one basic channel, so let's say S channel. So since the equation is linear, I can always normalize my answer in such a way that the right-hand side is just unity. That's the equation which we solve upon introducing this quantity. And looking at this equation, we immediately see that the temperature behavior of this quantity R is very simple. So look at this equation. What do we have? In the right-hand side is just unity. In the left-hand side, we have this quantity being acted upon by a certain operator, by a certain linear operator. Now the point is that the quantity itself is more or less structureless, because whatever we have in the right-hand side is an integral. And as long as this quantity is structureless, we understand that all the temperature dependence is coming from this pair of Green's functions. So this guy, it can have some dependence, but this dependence is on the momenta and frequencies. So I use letter K and P for both momentum and frequency. Meaning that actually we immediately understand that in the left-hand side, we are supposed to have the log coming from the log of t coming from the pair of Green's function plus some constant, meaning that our function at low enough momentum should be just this one, over this log times certain constant times plus some other constant. But this some other constant has to be equal to 1. We know this constant, if you will, from the boundary condition, because we understand that if our temperature is high enough, and remember that this guy is emergently small, meaning that at high enough temperature, this term has to be subdominant. We know the behavior at high enough temperature, meaning that we know that this numerator is exactly equal to 1, or accurately equal to 1, the accuracy being guaranteed by the smallness of this gamma, or if you will, by the smallness of this effective small parameter. So that's the beauty of using this function R as opposed to function chi, that now we have just two fitting parameters, one of which being the effective interaction. Of course, there is a necessary relationship between the parameters which we introduce in terms of the chi-naught and the parameters which we introduce in terms of the function R0. Here is the relationship. And essentially, here we go. So that's how we get the answer for the static response function, K0, chi-naught, which I introduced before, because you see the relationship, according to our definition of R, the relationship between chi-naught and R is by this integral. And this is precisely how we get this numerator. Because remember, as long as this R of k is structureless in terms of the k dependence, it does depend on temperature, but the dependence of k is essentially structureless. So the temperature dependence, extra temperature dependence of this construction comes from this pair of the Green's function. So precisely the same way it was coming over here. So the integration of this pair of Green's function introduces yet another, introduces yet another log in the numerator. So that's how we derive, ultimately derive this ansatz which I announced before. So, this one was just some spurious slide. So let me give you an illustrative example. So let me illustrate how this method works now for the uniform two-dimensional electron gas for a change. Before we were discussing three-dimensional, now let us apply the method to a two-dimensional electron gas. So here we have 3 plots. The first one just shows the static response function k naught of t as is, as a function of temperature in the logarithmic scale. So if you will, it's just the log of t. And you see, if we just look at this function, and here we do it for the S channel, we see that okay. So at different RSs, we do see some different behaviors, but in each case, our function increases with decreasing temperature. Here it increases slowly. Here it increases a bit faster. Here it increases more faster. So if we know nothing about the structure of this we cannot say anything we cannot deduce anything from those plots. Which one corresponds to Cooper unstable situation, which one doesn't? It's absolutely impossible to say. However, if we process our function, so you see what you see here is the following. So first of all, we exclude this log, and then we plot 1 over chi naught, and then all of a sudden, so what you see in this plot are just those 3 lines which seem absolutely similar. So looking at this plot, we would say that the behavior of these 3 regimes, those 3 values, closed values of RS, are pretty much the same, or at least we cannot tell any difference within this interval of temperatures. All of a sudden, we see a sharp qualitative difference, because the red curve, this one, being processed, just does not depend on temperature. And this guy corresponds to the quantum critical point at which the S channel experiences the transition from stable to unstable regime. This green curve goes down, and this upper curve goes up. So pay attention that what we've done, we just resolved 3 different physics regimes out of those 3 curves. One corresponding to the Cooper stable regime, this one corresponding to the Cooper unstable regime, and this corresponding to the quantum critical point. And finally, the third plot is demonstration that the quantity R0, the auxiliary quantity R0, which we used to actually derive the ansatz for the response function chi naught, is even better. So here we have just boring, if you will, straight lines demonstrating a very clear difference between those 3 regimes. So actually, with this kind of type of approach, we were able to construct the following phase diagram. So the only control parameter, as we already discussed before, is RS, the Wigner-Seitz radius. And those curves show the critical temperatures in 4 different pairing channels, S, P, D, and F, the main plot. So you see we are able to accurately resolve those quantum critical points with actually 4-digit accuracy. So once again, please do not kind of take this phase diagram as accurate with this 3-digit accuracy, because I just want to remind you that what was simulated was just the RPA approximation, which becomes accurate only in the regime of small rs. So this 4-digit accuracy is essentially the accuracy of extrapolation. So what I want to claim here is the ability to accurately extrapolate the finite temperature results to zero, essentially zero temperature regime, so that we can reliably identify those quantum critical points. Also, this inset shows the following. It shows those quantum critical points as a function of the angular momentum. So how those points behave for different L. So where are the points of instability in a given momentum channel. So to give you kind of, to impress you with the number, I can tell you the following. So with this technique, we can resolve the critical temperatures which are as small as 10 to the minus 100 of Fermi energy. So that's kind of the accuracy of the extrapolation. Yes?
Is the S-state nodal?
Say it again?
Is your S-state nodal, is it a higher harmonic of the S? Or because you only have repulsive interactions here, right?
Right, but it's a very special that's an excellent question. Right. So it's a repulsive interaction, but it's a very special because it's a Coulomb. It's an excellent question. It brings me to some other paper which I was not discussing. The Coulomb interaction is special because you see there is a retardation effect. So it's repulsive, but it's not boringly repulsive. It's not like short-range repulsive. And because of this retardation, the repulsive channel, well, the S channel, at least within the RPA approximation, becomes attractive, effectively attractive. It's qualitatively similar. So once again, I'm not claiming this as a physics result, because after all, it's RPA representation. But to give you an idea why this happens, it's just think of the standard phonon mechanism, which is all about retardation. There is a built-in retardation in the Coulomb interaction because it's long range, and you have, I say you can, but you have pretty much the same scenario. So it's gamma is essentially dynamic. It's frequency dependent, and this is the frequency dependence which converts kind of this channel into the attractive. Yeah, but once again, I cannot claim that what you see in terms of the S channel is the accurate controlled answer. But within the RPA approximation, we do have the pairing due to the retardation. Sometimes people call it plasmon, but I would not call it plasmon mechanism because obviously it's not a well-defined plasmon. Yes?
I was going to ask exactly this last point, whether it's similar to the plasma mechanism.
It's identical, if you will. It's identical. It's better to say it's what people call plasmon mechanism, but it's just a retarded form of the RPA, of the W line in the RPA representation. Yeah. Okay. Were there other questions? If not, it brings me to the conclusions. So the pair the pair susceptibility, the pair response function, has a very controlled ansatz, which allows us to extrapolate the Fermi liquid regime results for this function to arbitrarily low temperatures and to predict Cooper instability if it's there, or astability of the channel if the channel is stable. It's interesting that this, I don't know whether this fact has been discussed in literature. It's interesting that the Cooper stability is a sort of non-trivial physics phenomenon, because the response in the Cooper stable channel is different from the response of just an ideal gas, because we are used to think of the Cooper stable regime as if it's just a ideal Fermi liquid regime. It's not. It's something else, because in a Cooper stable regime, this log in the denominator ultimately compensates this log in the numerator, and the response becomes finite, while in the ideal Fermi gas, it diverges at 0 temperature. So this tool probably, as I already mentioned, can be used for quantum emulations. And there is something which is a sort of interesting problem, more general problem, which might be solved maybe by some of you. So you see, I was telling you the story about the spatially uniform perturbation. With ultra-cold atoms, people can probably create such a perturbation. Obviously, with electrons, we cannot create a perturbation which corresponds to 2 electron-creating operators in the bulk of a superconductor. But what we can do, we can sandwich our sample between 2 superconductors, and this corresponds to the famous proximity effect. So essentially, there is an experimental setup in which the pair creating perturbation is not uniform in the bulk, but it is sort of a boundary condition. And the question is, and I don't know the answer, and I invite you to think about it, whether we can generalize this uniform formula to the situation corresponding to the proximity effect. If it's possible to generalize it to something similar in the proximity effect, we will have an experimental tool of actually addressing the question of Cooper stability and instability, and also the question of critical temperature for the metals, say for gold, copper, some metals for which we don't even know whether they are Cooper stable or unstable at low enough temperature by the proximity effect. So what proximity effect is measuring, I'm reminding you, it just measures the effective Josephson coupling. And this Josephson coupling, in principle, should demonstrate the temperature flow. It should be a function of temperature. And if we know the ansatz for this function of temperature, and if this ansatz is similar to what you see on the blackboard, we should be potentially able to predict whether our sample, which is sandwiched between 2 superconductors, say 2 S wave superconductors, whether our sample will experience Cooper instability or not, and at which characteristic temperature. Thank you very much.
Again, I'm probably overdoing what I'm going to do now, but if I just take this formula and I say I have very strong repulsive interaction, this G is positive and very large.
Yeah.
And then I take T going to 0.
Oh, wait, it cannot be very large. It's supposed to be much smaller than unity, because the ansatz is the emergent BCS regime. Because if it,
okay, but so here's
it should be much smaller than unity.
That's fine, but does it need to be much larger than C?
No.
Because then if I send this to T equals 0, right, I get C over G, right, for my T equals 0 susceptibility. I'm wondering whether this could be, if C is still much larger than G, you could get a very large superconducting susceptibility.
Let me tell you something, which you will immediately buy. I swept it a little bit on the carpet, but with the good accuracy, actually, we know what C is. Remember, I was saying that the log in the numerator maybe I will show you the formula. I was telling you that the log in the log in the numerator. So let me comment on the origin of C. That the log on the numerator comes from this guy, but from this guy we know everything because it's just it's a Fermi liquid ansatz with Z factor and Fermi velocity. And at this point you can ask me why I write some letter C rather than the known answer in terms of maybe the one which you were writing in terms of the corresponding integral. The point is that there is a correcting term. That there is a correcting term because you see apart from the low energy part, there is also a high energy part. This correcting term is subleading. However, it makes sense and it's unknown, but subleading. But it's subleading only in terms of 1 over this log, meaning that it's subleading, but speaking practically, it's good to take it into account. So here is a direct answer to your question. So this C to the leading approximation is just a function maybe which you were writing on your slide. It's just the result of integration of a pair of Green's functions. So yes, the ratio will be very large. And this is very physical because you see to the leading approximation, it's almost an ideal Fermi liquid. So it has to be very large. The response will be finite but very large.
Why exactly Conel Overhauser? Why not some, I don't know, quantum single Tosia?
Yeah. Because we were not interested in doing some approximate. Ultimately, we are interested in doing controlled Monte Carlo, and the diagrammatic Monte Carlo. It's a remedy. It's a remedy. We just wanted to plug something which would be different from RPA to see the difference.
Basically, RPA with like some cosmetics.
Yeah, exactly. That's RPA with some cosmetics because it's not our final product.
Okay.
It was just the demonstration of principle. Demonstration of principle that this protocol which I described works. That's precisely the reason why I wasn't discussing diagrammatic Monte Carlo, blah, blah, blah. When we will produce a controlled result, hopefully, we will be dealing with just standard diagrammatic Monte Carlo protocol when we do order by order, control the error bars and stuff. That's the reason.
Questions? If I could ask one.
Yeah.
So imagine that you are pushing to the limit where your RPA approximation starts failing in terms of density.
Maybe it's already failing. I don't know.
Right. So what would be sort of the first order natural correction to the algorithm you presented to sort of accommodate for the...
It's important to emphasize that the protocol itself and the accurateness of RPA, they are apples and oranges. Because the protocol itself, it doesn't care of whether RPA is accurate or not. It just plugs some function which is supposed to be the Cooper irreducible gamma. When we will plug something else, the protocol will still be working because it's based on it's semi-analytic, if you will, because it's based on analytic considerations, right? What I was doing was not numerics, but from illustrations. I was kind of arguing why this function has this ansatz. This argument is purely analytic.
So I guess in this sense, one way would be just to modify the ansatz.
The way to control the error bars would be to do orders by orders and see whether the answer for the phase diagram changes or not. And if it does, to what extent.
More questions? If not, let's thank Boris again.